Assalamualaikum and salam sejahtera. My name is Amir Hafiz bin Zulkifli and my matrix number is 64623. Today, I will be presenting my final year project which is titled Ceiling Cooling Strategy using Radiant Technology in Buildings. So this project was actually supervised by Dr. Muhammad Iskandar Bijogli and it will be examined by Ms. Siti Nur Ain binti Musa as well as Dr. Aidil Azli bin Alias. So without further ado, let's begin. So this is the presentation outline that I have set for today. We will start with the introduction to the radiant cooling technology itself, and we will move on to the problem statements set for this project. From the problem statement, we can form a few objectives for our research, and then I will present to you the literature that I have studied in the preparation for this project, and then we'll move on to the methodology that I have set for this project as well as its expected outcome. Alright, so before we begin, I think it is important for me to introduce to you what the radiant cooling technology is. So this is a brief introduction. Radiant cooling technology basically applies the thermodynamics concept of thermal equilibrium as well as heat radiation. So bodies with a temperature difference exchange thermal energy until the temperature is equalized. So based on Stevens, a resting human male emits approximately 100 to 120 watts of heat energy through radiation. So approximately 45% of our body heat is regulated through radiation, which is considered the majority of the body heat. So a form of cooling technology that is installed in floor, ceilings, and walls. Basically, this technology, this radiant cooling technology, can be applied in floor, ceilings, and walls. But for the purpose of my research, I will focus on the ceilings. Alright, so I'm sure you're asking yourself, how does this technology work? Well, allow me to introduce to you the basic working principle of a radiant cooling ceiling technology. Alright, so as you can see here, there is a chiller which pumps mechanically cooled water into the pipes embedded in the ceiling panels. So basically, when chilled water passes through the pipes and it cools the ceiling, it converts it into a heatsink. So what do I mean by a heatsink? Alright, so the temperature of the ceiling will now be lower compared to the temperature of the bodies and the equipment inside the room. Now, heat energy will flow from a high temperature body to a lower temperature body. Thus, heat is now radiated from the occupants and the equipment inside the room towards the ceiling, which is why we call it a heat sink. Right? So the occupants now will lose thermal energy and they will experience a form of sensation in which we define as thermal comfort. Alright, so now why radiant ceiling cooling? Let's look at this from a benefits, constraints, pros and cons kind of view. Alright, so it is considered cost effective because it has smaller components in the system and it doesn't require frequent maintenance. It is also efficient in terms of its space usage because of the smaller components. So you would need fewer air handling units, which eliminates for air handling unit room. And it also reduces the mean radiant temperature, which allows consumers to experience thermal comfort even at a relatively higher air temperature inside the room. And lastly, it utilizes water as its working fluid, which is highly accessible as we all know, and it produces no harmful byproducts. And unlike conventional air conditioning, which uses refrigerants, and it also produces byproducts that are harmful to the environment. So the constraints of this system is that um, it requires dehumidification because surface condensation is a prime concern. So there are two types of loads. We have sensible loads as well as latent loads. So basically latent loads has to do more with its humidity and moisture level. Alright, so a radiant ceiling cooling system only deals with the sensible loads. It cannot deal with the latent load, which is why we need a dedicated outdoor air system that treats the latent load, or in simpler terms, it removes the moisture and it deals with the problem of condensation in the system. Alright, so these are the problem statement as well as its objectives. So this is the problem statement for our project. Well, we can see that the conventional use of air conditioners have actually been proven to be energy consuming and involves the emission of ozone depleting chemicals such as hydrochlorofluorocarbon. And when the ozone is depleted, it contributes to the change in climate and global warming, which we have seen the effects in the past few years. So the implementation of radiant cooling technology have actually been proven to be more energy efficient and environmentally friendly. So as engineers, we are obliged to choose the option that is more environmentally friendly, as well as it being more energy efficient. And not only that, this is actually parallel with the United Nations Sustainable Development Goals 12, which is responsible consumption and production, as well as SDG 13, which is climate action. Now, this is the objectives set from the problem statement that we have stated earlier. So the objectives that I have set for this project is for me to design a radiant cooling ceiling panel, in which we will refer to as RCCP from now on for our convenience. So it is designed using AutoCAD as a solution to the issue of heat gain in buildings located in Malaysian climate. Secondly, we will determine the cooling performance of the designed RCCP using simulation tools such as ANSYS Fluent. And lastly, we will observe the effects of implementing the radiant ceiling cooling system on the building energy performance using software tools such as OpenStudio. Alright, so this is the literature review. Now let's talk about the RCCP designs and its parameters. So Mohammed basically mentioned that there are three main panel designs, which are metal RCCPs, core-cooled ceilings, as well as capillary tube panels. So Jong and Mama, back in 2007, performed an experiment where they determined the parameters that played a huge role in the overall cooling capacity of a radiant ceiling cooling panel. And lastly, you performed experimental measurements to determine the effect of certain parameters such as tube spacing, tube thermal conductivity, plate thickness, as well as fluid flow rates on the cooling capacity of an RCCP. So the picture you see here on your right hand side is a simplified table, and it's of the design parameters set by Jung and Mama, and its percentage of contribution when it comes to the design of a radiant ceiling cooling panel. Right, now let's move on to the flow channel configuration arrangement. So as I mentioned earlier, the mechanically cooled water is passed through pipes embedded in the panels. So the way we configure the pipes also matters. So Radzai conducted a simulation that observed the temperature uniformity, which is essential when we determine the cooling performance of this. And he used three different serpentine flow channel configurations. So Mosa, on the other hand, in 2019, he simulated the temperature uniformity where not only the serpentine flow configurations were tested, but he tried two other designs, which is the canopy to canopy and tree-shaped flow configurations. And not only that, he even added the counterflow for each of the design. So to further see this, you can see on the right hand side, you can see the simulation of the temperature uniformity of different designs. So when you have serpentine, you have its counterflow serpentine, and so on. So as you can see here, the flow configuration that has the best temperature uniformity is actually in the counterflow canopy to canopy. Alright. So the important design considerations when we consider a radiant ceiling cooling system. So Ahne stated that radiant systems are only able to satisfy sensible heating loads. It is not able to deal with latent loads, and because of that, surface condensation is a prime concern, and thus we need a secondary air handling system that handles the latent loads. So Jin demonstrated a condensation prevention method by implementing a supply water temperature and fluid regulation system. So Song proved that by using a dedicated outdoor air system along with the radiant cooling system, it not only solved the problem of condensation by lowering the dew point temperature, but it also improves the responsiveness of change to internal load, and by using outdoor reset control and indoor temperature feedback control. Alright, now let's move on to the working fluid in RCCP. So I've mentioned earlier that most radiant systems, they conventionally use mechanically cooled water, which is basically water that is cooled in the chiller and it is pumped and flown through the pipes. However, there are studies that try to utilize other working fluids as an alternative to water. So Imran, in his experiment, he used water, but instead of mechanically cooled water, he used night cooled water, which is water left in the gutter, and it is cooled during the night and it will be used during the day. So the purpose of it is to reduce the overall operating cost, since we don't opt for a chiller, but we cool it naturally during the night. Jiang, on the other hand, performed a study where they observed the use of a refrigerant instead of water inside the radiant cooling panel. Alright, so now let's move on to the methodology of my project. Right, so this is the project flowchart and my approach for this project. So as you can see on the right hand side here is the flowchart for the project. So to achieve the objectives that I've set for this research, a project flowchart is actually needed. Why? So this is to ensure that the design and simulation of the proposed RCCP, they are performed in a more systematic manner. So the radiant cooling ceiling panel is designed using AutoCAD, and it will be transferred to ANSYS Fluent for the computational fluid dynamics or CFD analysis. Next, we will use SketchUp to create the geometry of the climate test chamber, and it will be transferred to OpenStudio to simulate the overall system cooling performance and energy consumption. So normally and typically people will use Energy Plus. However, OpenStudio is actually a software tool that has been integrated with Energy Plus, so I don't see that as a problem. Alright, so this is the proposed design of the RCCP. So basically it is a combination of the knowledge that I have based on previous studies. So as you can see here in the orthogonal drawing, you can see that the panel uses a counterflow canopy to canopy flow configuration, in which you have mentioned in the literature review earlier. It is proven to have the best temperature uniformity, which is considered beneficial for our cooling capacity. So the specifications of the proposed RCCP is as follows. So it is a 1100 millimeter long and 600 millimeter wide panel. It is of 3 millimeter thickness, and as I mentioned earlier, it uses a counterflow canopy to canopy pipe flow configuration. And for the pipe, it is the 9 millimeter inner diameter and 10.1 millimeter outer diameter for the pipes. So for the climate test chamber, this is the proposed setup. So as you can see here, we have the radiant ceiling cooling panels, and then we have the lights as well as the mannequins. So basically the mannequins will represent humans in an office setting. Next is the meshing of the climate test chamber. So basically the meshing of the climate test chamber was obtained from a research done by Lopez back in 2018. So as you can see here, this is the meshing of the mannequin, the whole climate test chamber itself, and as you can see here, the radiant ceiling cooling panels were also meshed. So this is basically the expected outcome for the meshing. Alright, so let's move on. Alright, so this is the expected outcome for my research. So based on the objective that I have set for this research, the expected outcome is as follows. So the first one is that the cooling performance of an RCCP is obtained through the simulation and analysis that I've explained earlier. So it will then be put into comparison with the cooling performance of a conventional air conditioning system. So secondly, the energy consumption of a system that implements RCCP will yield a significantly more energy efficient operation as compared to a conventional air conditioning system. So as you can see here on your right hand side, it is a calculated energy savings which compares the radiant ceiling cooling system with a conventional air cooling system. So this was a research conducted by Imran. So as you can see here, in terms of the energy consumption in kilowatts hours, you can see that there's a significantly huge difference between conventional air conditioning as well as radiant cooling technology, as you can see here. So when we look at the monthly operational cost, you can see that radiant cooling technology, when it is applied, there is a huge cost reduction when we compare it to a conventional air conditioning system. So as you can see, it is proven that radiant cooling technology, when applied, is more energy efficient and it is more cost efficient as well, which is why I believe that this technology is worth looking into, and it could even be an alternative, or it could be a replacement to the conventional air conditioning systems that we use today. Alright, so that is all for my presentation for today. I thank you for your attention and have a good day.